So we're going to finish this chapter up with looking at a Gilman's reagent, which is a lithium dialkyl cuprate, and then talk about some kind of key synthetic strategies when we're doing multi-step synthesis. So organocopper reagents are called organocuprates, and they consist of a really important kind of class of organometallic compounds. Among the most common are lithium dialkyl cuprates, which are a lot of times we'll say is like R2CuLi. These are sometimes called Gilman reagents. Again, we are trying to get rid of kind of this naming after people. This was named after Henry Gilman, who was an American chemist who lived from 1893 to 1986. To be more descriptive. So I want you to be able to recognize Gilman reagents, but know that these will probably always, from here on out, be called lithium dialkyl cuprates, just in the wider organic chemistry community. Every so often you'll have somebody who will kind of hang on to that old nomenclature. Now, as with other organometallic reagents, the carbon atom of lithium dialkyl cuprates, which are shown here and here, are electron rich because the carbon has a higher electronegativity value than copper. So you can see it's 2.55 here, and then copper is 1.90. And so as a result, these reagents can simply be described as R minus. Okay. This is really similar to Grignard's or alkyl lithium that we've seen previously. Now, lithium dialkyl cuprates are less reactive than the alkyl lithium or the Grignard reagents. And this is mostly because the copper-carbon bond here is a lot less polar than the one that we would see in the Grignard reagent or the alkyl lithium reagent. And when we say they're less polar, the electronegativity difference here and here are more than here. Okay. And so now, unlike alkyl lithium and the Grignard reagents, the lithium dialkyl cuprates tend not to undergo direct addition to a polar pi bond, right? So they're not going to undergo the direct addition here. Now notice we have one of those alpha beta unsaturated, these are conjugated, unsaturated carbonyls, okay? So when this alpha beta unsaturated carbonyl compound is treated with a Gilman reagent, right, which we see here as R2CuLi, where the R group here is CH3CH2, the R minus adds almost exclusively here at that beta carbon, right? So remember we have the alpha carbon and the beta carbon. Now, the reason for this regioselectivity is not exactly known because the specific mechanism for the reaction of the lithium dialkyl cuprates is not fully understood. So people are still researching this. However, more recently, chemists generally believe that the species that initially attacks as the nucleophile is not R minus. Instead, there's a key step in here of binding of R2Cu minus to the carbon-carbon double bond. And then that's followed by the transfer in alkyl group, but we really don't know, which to me is incredibly exciting. That's one of the more interesting things about science. Now, as we've previously seen with nucleophiles that add reversibly to the carbonyl carbon, the reversible nature of the initial binding can explain the tendency of organocupric reagents to react by conjugate addition instead of the direct addition. So that's the hypothesis. Now, I want you to notice that this is done at really low temperatures. You can see the conditions here are -78. Not all of them are done like this. But if you see conditions like this, what this means is they've placed a round bottom flask in a dry ice acetone bath. And that's to get to that -78. Then THF here is just the solvent. And then you will also notice here that we have an acid workup step, right? So just kind of be aware of that. Now, let's do an example. So we're going to predict the major product of the reaction below. And so when we do this, here's some things that we need to think about. So we need to first off recognize that this is an organocupric compound or a Gilman reagent. And so I just said we probably need to go away from calling that a Gilman reagent, but that's the way I learned it, and it's so hard to change, so I apologize. But what we should also realize here is we have an alpha beta unsaturated carbonyl compound. Okay, so we always need to evaluate our reagents that we start with and then our reaction conditions. So now that we've done that and we kind of know what we're doing, we say, how can we simplify the lithium dialkyl cuprate as an R- nucleophile? And so this is where you need to know that the R- nucleophile that we'll add is one of those that are in parentheses. So this is going to be HC3 minus, okay? Then you need to ask yourself, is this going to add predominantly by direct addition or conjugate addition? And remember, these lithium dialkyl cuprates tend to add by conjugate addition. And so that conjugate addition then points, so if this is the alpha, because it's 1 over from the carbonyl, this would be the beta. And so that's where it points to. And then the NH4 plus is going to act as the acid in the workup step, right? So we're going to have an acid workup. And then they ask, like, is the immediate product stable or does it rearrange? We're just going to ignore this. One of the reasons we ignore this is because if you look in the book, they try to explain this using a mechanism. And even though the book also says that it's probably not the R- that directly adds, they sure as shooting show a mechanism where the R- directly adds. So we are just going to kind of ignore that right now and just really view this more as a predict the product. So knowing that, we know that what we're going to see then is this molecule here. We're going to keep that OO double bond. We're going to keep this group here. And then the R group, that CH3, right here, is going to add right here to that carbon. Okay, so that's just something to be aware of. I will not ask you to do this mechanism because the mechanism is unknown. Now, one of the most important reactions in organic synthesis is the one between a carbonyl compound like a ketone or aldehyde that we've been studying through this whole chapter and either a Grignard or an alkyl lithium reagent. These reactions are important for two reasons, which are kind of shown here. First, they're important, and I don't love writing with yellow, so hold on, let me get that. I'll do purple, that's a fun color. First, they're carbon-carbon bond forming reactions, okay? So they can play a really key role in constructing a desired carbon skeleton of a target compound. So it's a way we can grow bigger molecules. Second, an OH group is generated at one of the carbon atoms joined by the new bond. So we can use the characteristic reactivity of the OH group to carry out further changes at that carbon. So two is they generate an OH functional group, okay? So I want you to notice this, right? So here, right, it's kind of like a 1-2 punch, right? You can come in here and you can add the R group here, and then you also turn this into a alcohol functional group, and then it could go on and you could use PBr and get an alkyl halide with a bromine substituent. That's section 10.5. You can use phosphoric acid with heat, and this will eliminate this OH through an elimination reaction. So because it'll form H2O and you'll produce an alkene, you can use the sodium hydride reaction and a alkyl halide through a Williamson ether synthesis, right? And make an ether. So this is very versatile. Both of these are very versatile in organic synthesis. Now, because the utility of the Grignard and the alkyl lithium reactions in synthesis, it's important to be able to undo these reactions comfortably in your mind to execute transforms efficiently in retrosynthetic analysis. These transforms can be carried out on essentially any alcohol by disconnecting the bond between the alcohol carbon and the adjacent carbon. Okay, and that's what you see here. So there's the alcohol carbon. This is the adjacent bond. We disconnect it here. We've undone a Grignard. Now we have our carbonyl and our Grignard reagent with that carbon metal bond. So, one precursor when we do this is going to be a ketone or an aldehyde, and the ketone or aldehyde is the carbonyl group that contains the alcohol. So where there's an alcohol, now you're going to have a ketone or an aldehyde. And then the other precursor is going to have the second carbon atom, right, that's directly disconnected from the metal atom. So we just break those apart. Now, because the target alcohol, if you notice, you could also disconnect it like right here, right? But this is symmetric, so it would give us the same precursor. However, if you have something that's not symmetric, then disconnecting a different carbon-carbon bonds can give us different. Okay, if that jumped around there, I was so excited about, and it might jump around on the next slide, I was so excited about this big reveal that I hit the button twice. So, different precursors. And this to me is really exciting as a professor, because if I were to give you this as a retrosynthetic analysis or a synthesis that you needed to target, you may say, well, I'm going to disconnect here, right, and use these two molecules. But your neighbor may say, well, I'm going to disconnect here and use these two molecules. And then your other friend across the room may disconnect here and use these two molecules, and they all would be correct, right? Now, please, please, please don't get caught up in kind of panicking over which carbon-carbon bond to disconnect, because it can seem really daunting at first, because now you have choices, right? The best way to handle this and get used to this is with practice, okay? So please don't get overwhelmed. Now, precursors. As we saw in section 18.8, which was 2 screencasts back, I think, a nucleophile can attack an alpha beta unsaturated carbonyl carbon at either the carbonyl carbon here, and that leads the direct addition product, or the beta carbon here, which gives us the conjugate addition product. Now, if we have a direct addition product, that's going to convert this carbonyl carbon into an OH group. Right there, okay? And that leaves the carbon-carbon double bond unaltered. On the other hand, with a conjugate addition, what we're going to see is that this double bond between the alpha and the beta carbon here is converted to a single bond here, and the leaving group, the C double bond O, remains unaltered, okay? So when you're undoing a direct addition or a conjugate addition in retrosynthetic analysis, be sure to look for the clues that can help you figure out which type of reaction is going to occur, okay? So, for example, in equation 1840, we're looking right here. This is our target that we're trying to synthesize. We have an intact carbonyl bond, and we have a nucleophile in the beta position. That means we're undoing a conjugate addition. I want to remind you, this is also called a 1,4. Okay. Notice that the cyano group, right, again, is on the beta. Okay. And so that gives you a clue as to the double bond's going to be on this side and not on this side, right? So see where the nucleophile has added. In the forward direction, this is what the synthetic step would appear like. So I just want to remind you that you write these in the forward direction with all the reagents as well. Now, let's look at clues for direct addition. So we looked at conjugate addition. Now we're going to look at direct addition. This is a 1,2 addition. So in the molecule here, notice the carbon-carbon bond is adjacent to the OH group. So you have a carbon with an OH group, and the next carbon over contains this double bond. This is the clue that the bond can be the result of a direct addition, particularly like with H- as the nucleophile. That would be a particular hint there, because we don't have much on the other side. So when we do, like, there's no R group here, right? So there's an H, there's no R group. So that leads us to believe that that's probably a sodium borohydride direct addition. You could also use lithium aluminum hydride. Ooh, said that real confidently, but now I'm nervous. If you wanted to. Yes, okay. I feel, I'll double check that, but okay. So in the forward direction, you would see this. Now, if a particular synthetic analysis suggests the use of an R- nucleophile in the forward direction, we have to consider regioselectivity a little bit. So for example, let's say here that we're going to carry out this transform, right? And the precursor is an alpha beta unsaturated ketone and an R- nucleophile. Okay. In the forward direction, the R- nucleophile can take a variety of forms, like an alkyl lithium or a grignard or a lithium dialkyl cuprate. We want the nucleophile, though, to attack the beta carbon, which, remember, is this carbon right here. So there's our alpha carbon and there's our beta carbon, because we want the R group to add to that carbon all the way through, right? And so we would choose the lithium dialkyl cuprate, which gives us almost all the conjugate addition product, adding at that beta carbon. So you do have to be savvy. You do have to think about it. You've already seen where I said something that I had not looked up in a while, right? And I had to really, really think about it for a second. So even with a lot of practice, we still have to go back and we have to look. And again, you are going to get the hang of this. You will be fine. Now, talk for just a second about kind of let's stop and let's think about what we've learned in organic chemistry so far. Okay. And in this chapter, we've learned that alkenes can be synthesized by the Wittig reaction, which is what you see right here at the top. There's a Wittig reaction and we've synthesized an alkene. Okay. But maybe you're thinking, hey, Dr. Pierce, in chapters 8 through 10, we saw examples of alkene formations by E1 and E2 reactions. So why should we use the Wittig over an E1 and E2? Well, the Wittig is generally viewed as more synthetically useful, because it's got a lot of specificity, sorry about that. And what I mean by that is in the Wittig, this carbon-carbon double bond forms precisely at the location of the carbonyl, okay? In E1 and E2 reactions, you generally get a mixture of alkene isomers, and occasionally the desired isomer is the minor product. So for example, if this is what we really want to form, this is going to be our major product because it's a more substituted alkene, which makes it more stable. Okay, so this is problematic for us. And so most often, if you have a choice, a Wittig reaction is a better reaction to use. And it's not always, but I would say 90% of the time it is. And so a lot of being an organic chemist is viewing things like a puzzle. And you have to figure out how you want to put it together, and you have to be kind of savvy about what your percent yields are. So it's important for us to know that both of these reactions, right? Because in some situations, the E1 and E2 may be better, okay? But, for example, maybe this is the product you desire and you only have this in your reagent drawer, right? But that being said, right, if you get a lot of choice, a Wittig may be a better option, but it's important to know both. Now, just other kind of yield issues when we talk about this. This is 2-bromo 1-cyclopentylpentane as the precursor here, which is a little different than not much different, but a little different than the one on the previous slide. If this is used as a precursor, there's a problem because you can get both elimination products or dye substituted here. And so that means you're going to get a significant amount of each. And so, again, synthesis are better when you don't get multiple products. When you can mostly get the product that you're trying to synthesize with very few other side products. And the Wittig does a better job of that than these E1 and E2 reactions. So the Wittig reaction is just usually, not always, but usually the better choice to maximize percent yield in the desired reaction.